conjecture, Marden's tameness conjecture. And it says that, I'll just say it, so it says if gamma in PSL2C is a finitely generated discrete group, actually I guess I should say for the experts torsion free, otherwise we don't get a manifold. So then the quotient 3 manifold, hyperbolic 3 space mod gamma, is tame. And what tame means is that it's homeomorphic to the interior of a compact manifold. And so I should say what all the words mean. But so PSL2C, let me sort of, before I go too much further, PSL2C, as I assume we all know, can be thought of as the isometry group of hyperbolic 3 space, I guess orientation preserving, but it can also be thought of as the Mobius transformations of the Riemann sphere, and the Riemann sphere acts as a sort of boundary to hyperbolic 3 space. And this already, and so gamma is a discrete subgroup in here, so it acts on H3, and you get a quotient manifold. And this already encapsulates a lot of what's interesting about this field. We have, already in this picture, you see geometry, of course. You see complex analysis, as you saw in Peter Jones' lecture. There's no cosmology, though. Sorry. And you see topology also, of course. And let's see, what else do you see? And you see dynamics. Where are the dynamics? Well, here's an infinite group, typically infinite group acting on a compact space. So there's naturally going to be interesting dynamics. So it's somehow the mix of all these ingredients that makes this a great subject to think about. Now, the statement of the theorem, and I forgot to put the authors on. So maybe you've heard of these authors. So this is Ian Egel, Danny Caligari, and David Gabay. So how do I move this thing? Is there a... Aha. Okay, so that's the theorem. And it looks deceptively topological. It's the interior of a compact manifold. So one of the things I want to convince you of is that this topological statement actually has geometric content, and I want to talk about what that geometric content is. I won't do it yet, but there's sort of geometric tameness, which is a kind of more, apparently stronger statement about the geometry of these manifolds, and it has many consequences, one of which is the Alfor's measure conjecture, which I guess Peter stated. Actually, did he state it? I think he stated it, yeah. Sort of a 0-1 measure statement for the limit set of this action. It has properties, it has consequences for the deformation theory of Kleinian groups. Kleinian groups are just such groups. Those are called Kleinian groups. And other, sort of a whole long list of consequences for 3 manifolds and for geometric constructions with 3 manifolds. So I want to somehow give you a feeling for how this fits together. And it seems to me that before one can really discuss tameness, one really has to talk about the lack of tameness first, so that we know what it is that we are fighting against. So I want to spend a little while making non-tame manifolds, 3 manifolds. So it's important here to say that gamma is finitely generated. If you had an infinitely generated group, I mean, you could sort of do anything with an infinitely generated group. So let's build non-tame manifolds with finitely generated group. The first known such example is due to Whitehead. Actually, I won't do this example because I'm going to do a couple of others that make it, that come from it. But Whitehead built a contractible 3-manifold, which was not homeomorphic to three-dimensional Euclidean space, and it came up because it was sort of one of the ways in which his program for proving the Poincare conjecture was not working. So that's an example of a manifold with trivial fundamental group that's nevertheless not the interior of a compact manifold. I'm going to do so now I want to give you an example of a manifold whose fundamental group is non-trivial. It's just say the free group on K generators. So that if you spend 2 days studying 3-manifold topology, you quickly find out that there's a theorem that says that a compact manifold with free fundamental group, a compact 3-manifold with free fundamental group, is just a handle body, a ball with handles attached. So I want to give you an example of a manifold with the same fundamental group, which is not the interior of a handle body. So this is, I think, appears in a paper of Tucker, and it's the following construction. And it's very similar to Whitehead's construction. So that's why I'm not doing Whitehead. So start with a handle body of genus K. So let's, here it is. So let's call it H. So I'll draw this in genus 2. And then embed it, call this map G, into itself. But I'll draw itself again a little bigger. And then maybe let's see. That was great chalk here. So maybe I'll draw the first copy red. And then I'll embed the red one in here, except I'll do it in a slightly complicated way. So let's see. So maybe like this. So here's the first half of the handle body. I'm making it sort of thin. And then the second half, instead of just coming around like this, I'm going to make it have knotted in some way. Okay, so thicken this red chalk here and make a handle body. And that gives you the embedding of this red thing into here. Is that clear, what I'm doing? So that's a map G. It has the property, so this is still H, I guess. It has the property, if I did this right, this has the property that the boundary of H is incompressible. This means pi1 injective in H minus the image of the map G. And moreover, pi1 of the boundary of H, so it injects, that's the incompressibility, into pi1 of H minus GH. I guess I should have just written that first. But it injects, but it does not surject. So this is not surjective. Okay, so it's not, I'm not going to prove that for this example, but it shouldn't be hard to see because of the nodding that it's true. Having produced one such embedding, I can just repeat this embedding. I can take this H and map it into H again, except this new H will be green. Actually, this one was green, maybe. And then the next one will be purple. It's great to have all these colors. And so the green guy goes into here the same way as before. So I'm going to try to draw it without. Okay, here's the purple handles. And inside the green is the red guy, right? Still in there. But now it's kind of knotted itself, and then it's going through this knotting. So you see that things are getting more complicated. Okay, so I repeat this procedure. When I was first a parent, I learned a rule about kids, which is you never do anything with a kid that you're not prepared to repeat 10,000 times. So that's what you do. So you just keep doing this, and you take the limit, the direct limit of this sort of I'm not sure how to write this, but of this kind of, you have this kind of, you repeat this map over and over, and you take the direct limit. What it really means is just that you assemble all these objects together. When you put this in here, you can think of this one being a superset of this one. So it's like you get a bigger one, and then those guys together are inside this even bigger one, and so on. They kind of expand outward. You have to change your point of view, and so you can think of this. Maybe we'll number it. We'll think of this one as handle body 1, this is handle body 2, this is handle body 3, and you just take the union of all the handle bodies. And that gives you non-compact 3-manifold. Now, what do I have to convince you of? Well, note that although we had this sort of slightly tricky property here of the embedding, on the level of fundamental groups of the original thing, if you don't subtract anything from the image, if you look at the map, say, pi1 of H1 into pi1 of H2, this is the map G star. This map is just an isomorphism. Right? because the knotting didn't affect the map on fundamental group when I think of it this way. And so in fact this map is just the map from H1 into M is in fact a homotopy equivalence. It's not hard to see. And in particular, it's an isomorphism in fundamental group, essentially because by repeating this point. So this thing has the same fundamental group as this. And why is it not tame? Why can't M be made the interior of a compact 3 manifold? So M is not, say, the interior of some compact N because, and this is the same observation that Whitehead had in his example, because if you throw away the first one, so if you look at M minus the first handle body, which is a compact subset, this has a fundamental group which is infinitely generated. And why is that? Well, because if you throw away the red from here, then what's left in here is this fundamental group of the difference, which is bigger than just the fundamental group of the boundary. And then when that goes into the purple one, you get an extra piece which also has fundamental group, which is not obtained from what was previously produced. So maybe should I not use this dark third of the room? I don't know. Can everyone see this board? Okay. So I want to draw a slightly different schematic of what's going on here. You can draw H1. This is a cheat that people often do in this little subfield. Is you draw a handle body this way. You think of this as the boundary of the handle body, and you somehow pretend that it looks like it's like looking at the handle body in profile. So this is H1, and then I'll stop with the colors. Here's H2, and here's H3, and so on. So at every finite stage, it's a handle body, but you keep adding these pieces on. Each piece that you add on is that difference between the green and the red, repeated. And so the fundamental group of each piece is not, it's not generated by its boundary. So there's extra stuff in each one. And Seifert Van Kampen tells you that when you put them together, you get something non-tame. You get something with infinitely generated group, provided that this part is gone. Because these boundaries are all pi1 injective, so you can apply Seifert Van Kampen. Okay, that's the basic example. Let's call that example 1. Okay. It's example 1. Now, let's see. You could still say, well, it's not so terrible. It's just a union of handle bodies of genus 2, of the same genus at the beginning. So what could you do that's worse? So let me show you one thing that's worse, and it'll kind of be relevant to think about later. So again, this example is exhausted by a sequence of compact handle bodies of genus 2. So let's try to make something that can't be exhausted by handle bodies of genus 2. So maybe we'll do it like this. We'll take H1 the same way as before. And then we'll map it, instead of into a genus 2 handle body, we'll make H2 a genus 3 handle body. Okay, and then let's see. And we'll put it in. I'll probably get this wrong, but let's see. Maybe we'll take the first handle and wrap it around like this. And then the second handle, is this what I want? So I guess I want it to go around this part, but I also want to somehow loop around the rest of it. So I'm going to try to do this right, but I doubt that I'll succeed. So maybe something like this. I don't know. So maybe I'll knot it around some number of times over here. I can sort of do whatever I want, right? So I don't know. Maybe something like that. It's more complicated than it needed to be. But what have I done? If I do it right, I still get pi1 injection of this group into here. It's still going to be true. If I put in enough complication here, it'll still be true that the boundary of this one is incompressible in the complement of the red. So this incompressibility is still going to hold. So and moreover, because of all the knottedness, when I throw away the red, I get a more complicated fundamental group than whatever was generated by the boundary. So so I still get a sort of similar thing, and I'm going to continue. That was probably much more complicated than it needed to be, but now I've added genus. So so there's a problem, which is now this is no longer a surjective map. The red to the green is no longer a surjective map on fundamental group. So I need to kill the extra stuff. I've got an extra generator, so I could easily do that. Let's do one more stage of this. We'll take a handle body of genus 4, and now this was the green handle body here with 3 holes. I'm going to map the 3-hole handle body like this. Say the first hole goes here. Say the second hole goes here. I thicken that up. And the third hole, I want to kill it somehow, but I want to. So let me just draw it. I'm going to maybe do something like this. So it kind of looped around and traveled through the rest of the handle body. All this was to make sure that the boundary of this thing is now incompressible in the complement of the green. Okay. But this has the feature that if you look at this green loop is null homotopic inside the bigger handle body. So I've killed this extra fundamental group that I generated at this stage, and then I keep going. I can keep making the genus larger. I keep introducing more fundamental group at each stage, and then I kill it at a later stage. And so it's still true that the manifold I get has free fundamental group of rank 2. Okay, but now this you have to check. There's some kind of exercise here. If I do this right, it will no longer have an exhaustion by genus 2 handle bodies the way that the first one did. Okay, so this is a non-tame rank 2, but has no exhaustion by genus 2 handle bodies. So that's the situation. If you're trying to build non-tame things, you start to build things like this. And I'm not going to give any more examples, but that's kind of the enemy if you're trying to prove tameness. Okay, so actually, we're not done with topology yet. So there's one last topology statement we need before we go to geometry, which is what do we know about these manifolds? Well, what we know is that's it right here, the Schottky theorem says, so this is Peter Scott, says that if M is a 3 manifold and it has and pi 1 of M, actually, sorry, we should also add a technical condition of irreducible. This roughly means the second homotopy group is trivial. This is somehow automatic for all the manifolds we're going to think about, for hyperbolic manifolds. So if it's an irreducible 3 manifold and the fundamental group is finitely generated, then M contains a submanifold that carries all its homotopy. So M contains a compact 3 manifold K such that the inclusion map from K into M is a homotopy equivalence. So schematically, we draw it like this. Here's K. It's a compact manifold with boundary. Its fundamental group is the whole fundamental group. And in fact, the whole manifold retracts to K. But somehow, what's happening in the rest of the manifold could be mysterious. And that's exactly what happened in both of these examples. In both of these examples, in this example, H1 was the core in this sense. This thing is called a compact core. Okay? So in the first example, any one of the HNs could have been a compact core. Any one of them was a manifold that carries all the homotopy. In the second example, this one was a compact core, but none of the other ones that I drew are compact cores because their inclusion eventually, a lot of the fundamental group here is eventually killed as you include them further on. Okay, so that's Scott's core theorem. We're still in the 70s in this discussion. Okay. So Okay, so those are all the bad things that can happen in topology. And I guess if we're trying to understand, I mean, essentially, the one last thing to say about this picture is that if you're trying to prove this manifold is tame, what it amounts to saying, so tameness, is equivalent to the statement that there exists a core K such that the complement of K is a product, boundary K across the real line. Okay, that's really what we're looking for. Note that I said exists a core because the cores are not unique. Of course, they're certainly not unique up to isotopy, but even so, you could, just like we did here, you could knot these cores in different ways. So it's not always, you have to choose the correct core. That's one of the issues with proving tameness. Okay, so this is the topological situation. So now what about geometry? So maybe let's do the most trivial case first. So suppose that the fundamental group is just trivial, then of course the manifold is just H3, and it's a ball. I mean, it's the interior of the 3 ball. So there's sort of no Whitehead hyperbolic 3 manifold. The next, let me jump sort of a step. Let's make gamma a Schottky group. So I have to tell you quickly what a Schottky group is. I'll just draw the picture mostly. So take hyperbolic 3 space. And this is going to be a free group. So it's going to be a free group generated by K elements. And they have to have the following property. You look at, so every element, a generic element in PSL2C is going to be a translation, maybe with a screw motion. And so it's going to have an axis. So I'm just sort of assuming everybody's willing to believe all this if they haven't seen it already. So here's G1. It translates along this axis, and maybe G2 translates along this axis. Okay, the points are out on the sphere, on the 2-sphere. So it translates some amount. Suppose I have this picture. Let's just draw the 2-generated picture again. And if I choose them in such a way that this translation takes a disk over here. So this is a hyperbolic plane that's sitting here in hyperbolic 3 space, and its image, if I chose, say, one that's orthogonal, its image will be orthogonal to the axis again, and it'll be over here somewhere. And then there's a similar picture here. So in this picture I've chosen to draw, these 4 half balls have a common exterior, which is this blue region. We'll call that F. And it's not so hard to see. First of all, it's not so hard to see that this group, the group generated by 2 such elements, is discrete, is free. And the quotient is just what you get by taking F and gluing these disks to each other. So take F as the ball minus, scoop out these half balls over here, and then glue this to this and this to this. You get a handle body. So H3 modulo gamma is equal to F modulo the gluing, which is just a handle body. Oh, and this is an open handle body because I haven't included the boundary. But it's the interior of a closed handle body. Okay, so that's the simplest case. I'm going to erase these non-tame examples. Oh, I keep forgetting this. Okay, so what is the issue? So, okay, so all these Schottky groups are tame. And actually, for the rest of the talk, I think I'm mostly going to talk about free groups, because although free groups are the simplest group in some basic sense, they're also the most complicated group. And it turns out everything is about as hard for free groups as it is for anything else. In fact, harder. So let's think about free groups. So you'll note that when I did this, it's pretty clear, I think, from this that there's an open set of such groups if I allow the generators to change in the group in PSL2C. Because, of course, if I perturb this slightly, this picture will stay. So the only problem is what happens is if I bring these axes close together or I shorten the translation length so that these things start to intersect, it becomes a little bit unclear what happens to this topology. So in the deformation space of the group, so there's Ham of the free group into PSL2C. I guess you could mod out by conjugation if you want to avoid things that are just trivially the same. But Anyway, inside here you can think about the Schottky groups. And they're an open set. That's not so hard to see. But the boundary of this open set, the boundary of this open set also consists of discrete faithful groups. Also consists of discrete faithful groups. This is, depending who you ask, so this has, this is essentially what geometers know as the Margulis lemma, and what I guess dynamicists known as the Margulis-Kazhdan-Zassenhaus lemma, or the Jorgensen inequality. So it's a discreteness criterion for groups, and Chakro showed that discrete groups have this property that non-elementary discrete groups, if you take a limit of them, they converge. If they converge at all, they converge to a discrete, non-elementary discrete group. So the set of discrete things is closed. So that means that in this fairly decent-looking manifold, just all these maps from FK to PSL2C, there's some open set, maybe unbounded, and on its boundary, which we know now is quite complicated, there's lots of other groups that are still free, but much more mysterious. And it's about these that the conjecture is really involved. It's sort of, this is the issue. So I want to tell you, how much time do I have left? Like 10 seconds or what? At 5. And we don't have to eat till 6, so I'll just keep talking. Yeah, okay. Okay. Okay, so yeah, I was hoping to tell you a little bit more than what I've told you. So let me go just on a little bit more. So how do we deal with how do we understand these manifolds in any sort of way at all? So let me give you one more example of a hyperbolic free manifold. This one will not have a free fundamental group. So it's the following. If you start with a manifold M that fibers over the circle. So I think of M as, you can think of M as a surface, say F cross the interval modulo some identification psi from F cross 0 to F cross 1 if you want. So it looks like this. So you identify these two and you get something that fibers over the circle. And this is obviously a hyperbolic manifold. So Thurston showed that Thurston's geometrization conjecture, even pre-Perelman, applies to these examples, and it shows that if psi satisfies a certain condition, which we'll just call pseudo-anosov, we won't worry about the details, then M is hyperbolic. So there's a hyperbolic manifold that's homeomorphic to this thing, and then it has an infinite cyclic cover. So in fact, let's just draw it here. If you just unwrap this circle direction, you get an infinite cyclic cover with this kind of periodic structure. And this thing is the group associated here is just the fundamental group of the surface. It's a finitely generated group. And it's also tame. It's just a surface cross R. Right? This is F cross R topologically. So here's another example of a tame manifold. And it's somehow geometrically very different from this one. Maybe, let's see. So maybe I haven't quite explained what the difference is, besides the fact that the groups are different, of course. Let me try to say this very quickly. So, well, let's see. So one thing you can sort of see from this example, maybe, if you think about it, is that as you go to infinity in F, like this, you sort of lose the group. You see that the injectivity radius of the manifold goes to infinity as you go out here. And the manifold is spreading out in a strong way. In fact, what happens in this case is that the manifold itself contains a compact, convex subhandle body, and the exterior of it expands exponentially outward as you go out. So it's not completely obvious from this picture, but it's not so hard to see. So this has sort of a compact convex core to it, whereas this one does not. This one somehow seems to be complicated forever and ever as you go to infinity. And Thurston first analyzed these sorts of manifolds, and from this one gets a kind of dichotomy of possible types. So let's say it this way. So I'll try to make this is kind of a quasi definition. I'm not really being precise. So an end of a hyperbolic manifold n is first of all geometrically finite. So let's call the end E. What is an end of a manifold? It's just I didn't really define an end. You should think of it kind of informally this way. You have this core, compact core of Peter Scott inside the manifold, and then it divides the manifold into a bunch of non-compact pieces. Okay, and each one is called an end. That's roughly the idea of an end. An end is really an equivalence class of such things, but it's a direction to go to infinity, and this is the thing we're trying to analyze. So an end is geometrically finite if there exists a core K with convex boundary component facing the end. So the picture here is this: that if I can put in a surface here on my core, which is convex in the standard geometric sense of convex, then this end is called geometrically finite. What happens in this case is that convexity tells you that if you look at the distance function from a point here to the boundary, convexity tells you that the gradient flow for this distance function gives you a foliation by gradient lines and by equidistant surfaces. So there's a natural product structure on a geometrically finite end. It's simply degenerate and this is going to be hard to state precisely, but if the end, let's actually for the moment include the tameness assumption in here. So surface cross R, the end is actually a tame end, and there exists a sequence of hyperbolic surfaces in E homotopic to, let's call this S cross 0 infinity, homotopic to S cross 0 in E and leaving every compact set. So this definition is due to Thurston and Canary. Thurston introduced this idea for manifolds with incompressible boundary, and Canary refined it and worked with it for the case of manifolds with compressible boundaries, such as the handle body. So in this case, this is the picture that you're supposed to imagine. There's no convexity of the core. There's just some core. And then, as you go out the end, you can keep finding certain surfaces. And I didn't say what a hyperbolic surface is in this case. You should think of it as follows. You should think of it as an immersed surface or somehow reasonably mapped-in surface whose intrinsic metric is close to hyperbolic. So, for example, cat minus 1 would be cat for those who know what this terminology means, a cat minus 1 surface, or even if it was an actual hyperbolic surface, a surface with intrinsic negative curvature. If you could find a sequence of such surfaces going off to infinity, then we call this end simply degenerate. I'm cheating a little bit. Well, first of all, I'm being vague about the definitions, but also I'm not, this definition is not correct if the manifold has cusps, but there are no cusps in this lecture. So for experts, you have to fix all the words slightly to make it correct. Whoops. What did I do wrong? Oh, I can't move that one? All right, let's go somewhere else. So this one, the Schottky groups have ends of the first type, and these infinite cyclic covers have ends of the second type. You can sort of, it's not that hard to convince yourself if you just, here's a way to see this in this case. Go to this manifold, take a fiber, and it's compact. It's not that hard to find a minimal area surface in this homotopy class. So there's a minimal surface, certainly a minimal surface is going to have intrinsic negative curvature, so you just lift it up to here. But up here you have infinitely many copies of it marching off to infinity, all of them homotopic. So this does certainly have a sequence of hyperbolic surfaces in it that go off to infinity. It was sort of somehow the realization of this earlier work was that this was a sensible condition. You could A, expect this to happen, and B, you could learn things from it. So in fact, you could actually, it turns out, if you think about it a little more carefully, you can weaken this condition. I sort of wrote it this way. I sort of included tameness, topological tameness, in this condition. You can actually weaken this if you just have the sequence and they are homotopic without this assumption. You can conclude from this that the manifold is in fact tame, that the end is a product. So in fact, it's sort of it's a non-vacuous statement that if you say it right, this geometric condition implies that the end is tame. So we call this, so we say that n is geometrically tame if all n's are of type 1 and 2, again in the case without cusps. And it's not so, and kind of the first step is to show that geometrically tame implies topologically tame, which is the Marden property. That's sort of the discussion I had over there. And then Canary showed that the opposite is true. Topological tame implies geometrically tame. So that means that this is really what we're looking for. So these are really equivalent conditions, and we should be proving this geometric property. And it's sort of this kind of property that you can expect to have geometric consequences. So maybe, so for example, there are spectral consequences. If you look at, if you think about eigenfunctions of the Laplacian in this manifold, then they produce volume increasing or decreasing flows, or volume preserving flows. They're gradients. Flows are volume, have a certain property with respect to volume. The existence of these negatively curved surfaces in the manifold, these are barriers of bounded area by the Gauss-Bonnet theorem, and so they control the possible eigenvalues of such functions. So you have consequences for the spectrum of the Laplacian, which have been worked out by various people. I guess I'm not going to be able to say much. And this is sort of where the implication for the Alpers measure conjecture comes in. The Alpers, I guess I didn't state the Alpers measure conjecture. It's a statement about the measure of the limit set of the group at infinity. But but Thurston showed that for these sort of n's in the incompressible case, if the Alpers measure conjecture fails, you can construct certain harmonic functions in the manifold, which are then ruled out by the presence of such n's. So that's one sort of type of geometric consequence that follows from this property. Okay, let me try to say. Can I take 5 more minutes? Is that acceptable?
20 minutes. 15 is fine.
When did we start?
45. So if you want to be,
Oh, I see. Okay.
If you want to be a real professor, you have 10 minutes left. That's the 15 minutes.
I see. Okay. Can I give a quiz? Okay. So now that if everybody's memorized the statement of the theorem, okay. So let me try to at least. Not only is there one proof of this theorem, there are two proofs of this theorem, which are which have common elements, but they're really two distinct proofs, and I'm not going to be able to, trying to discuss them both is difficult. So what I thought I would try to talk about a tiny bit is is like at least one ingredient that goes into these proofs.
You started at 10.
I have 20 minutes. Okay, that's okay. Yeah. All right. Well, I'm still only going to get to one tiny thing. So, actually, I think what I want to say something about the proof of is a theorem of Soto, which preceded the proof of the full theorem and sort of plays a role in it. So I'm going to let me try to state that theorem. And then I'll say a little bit more maybe. So Soto proved a few years before the following statement: if n are same, so same setup as before, finite degenerate group has an exhaustion by compact cores. I assume that the audience also has an exhaustion by compact cores by now. So this is the setup that we had. This was example number 1, right? We had these sequence of genus 2 handle bodies. Each of them was a compact core, and they exhausted the manifold. So if n has an exhaustion by compact cores, then it is tame. Okay, and then and we'll just do that. We'll talk about this just in the case of the handle body, so or the free group. So let's think for a minute what happens. And I'm actually, to be honest, I don't remember the exact details of Juan's proof, but I'll try to. I have sort of reconstruction, which I think hits the main point. So here's the idea. So we have. Let's draw our manifold. So here's a compact core, and then we have an exhaustion by compact core. So let's sort of draw. You might as well assume that they're just nested like this. So we have some kind of picture like this. So this is sort of the boundary of Kn. And each one of them is a handle body of this type. But remember that we're worried that somehow inside, in between them, there's some non-trivial topology, just like there was in the first example. Okay. So let's. So step 1, which I'm not going to justify yet, I'll come back to it. Suppose each boundary Kn is homotopic to a negatively curved surface so this one doesn't have, this is an embedding. This one doesn't have to mean embedding. Let's call it sigma n, which is mapped into n. And actually, homotopic now, let's be very careful about this. Homotopic outside of K. So we're going to try to do everything. We know that all these surfaces, certainly in the example we started with, all these surfaces are homotopic to each other in the manifold. But in order to do the homotopy, you have to cut through the entire knotted colored chalk in the beginning and come back out. So if we avoid K, then these guys are not necessarily homotopic to each other. And we're going to consider homotopies in there. So if you look at homotopies in the complement of K, suppose that each boundary surface is homotopic to a negatively curved surface, say sigma n, which is immersed. So and moreover, let's suppose that such that the sigma n's leave every compact set also. Okay? So I'm just supposing this. We have to, of course, establish this, but let's suppose it was true. So that's step 1, is to generate that. So somehow I didn't know anything about the geometry of these things, but now each one is kind of homotopic to something which is geometrically controlled. It has negative curvature. Suppose that was true. Then I'll end up cheating at some point soon. Then I want to claim the following thing. I want to claim infinitely many of the sigma n are homotopic to each other in the complement of the compact core. So I can actually map these to each other. And of course, that would imply that infinitely many of the original ones are homotopic to each other. And that basically finishes the story. If I could show that these are homotopic to each other, say infinitely many times, then I've got these embedded surfaces that are homotopic to each other. And then it's not so hard to prove that between each two such homotopic surfaces, there is a product region. This becomes a more standard three manifolds problem. So why is it true that these guys should be homotopic to each other? So the proof here is an interpolation trick. So for this, I have to tell you some version of what I mean by negatively curved surface and explain to you how to connect them to each other. So let's try to actually make a concrete negatively curved surface. So this will take a couple of minutes to explain what this is. So what I'm going to construct is a simplicial hyperbolic surface, which is one type of negatively curved surface. In the following way. I want to build, the idea is going to be this. A simplicial hyperbolic surface is basically a triangulated surface which is mapped in so that every triangle is totally geodesic. Okay? And there's one extra little negative curvature condition which I have to say. So this is going to be a surface equipped with a triangulation T and a map, say H, from sigma to n, such that each triangle, so let's say H is totally geodesic on each triangle. And therefore, it makes each triangle into a hyperbolic triangle. And then the sum of the angles at each vertex, I guess sigma was a bad name for the surface, sorry. Sum of the angles at each vertex is at least 2 pi. So that turns out to give it kind of its negative curvature properties. A sort of easy way to build one is the following. You take your surface and you pick one closed loop on the surface, and then you say take a vertex on that closed loop and triangulate the rest. So maybe it looks like this. So you can imagine what this looks like, right? I can sort of keep putting in edges until I get a triangulation. And then, and I've got this one distinguished loop alpha. And then I choose the map H in the following way into my manifold. Suppose I started with a particular homotopy class, and I want to make it simplicial hyperbolic. So I start with this picture, and then I draw, say, the curve alpha. I map it to its geodesic representative, alpha star. And then I tighten everybody else. So I take this vertex, and I map it to the geodesic associated to it, and so on with every loop. And then it turns out that the triangles in here, there's only one way to map them in so that they become totally geodesic. So I just fill everything in, and I get a surface which exactly satisfies these conditions, where this 2 pi condition follows from the fact that at the vertex, there's only one vertex. At the vertex, I already have a smooth geodesic passing through it. So if I add up all the angles around this, or all the other triangles, they must add up to at least 2 pi. So that's one easy way to produce such a thing in 1 minute. So what's the point of this? The point of this is that there's combinatorial data which produces a geometric surface. And the geometric surface has all the nice properties we might want, such as area is bounded by Gauss-Bonnet, diameter is bounded, or rather diameter outside the thin part is bounded. So there's various geometric constraints on this thing, which I'm going to kind of use in passing in a minute. And so now the idea is that what's the interpolation trick? Well, you can just, given one such thing, you can make another one by changing the triangulation. So elementary moves on the triangulation produce controlled homotopies of simplicial hyperbolic surfaces. Okay? So this idea comes from, again, from Canary's thesis. And I guess from Bonahon. I didn't mention Bonahon enough in this talk. The original tameness theorem, I should have said, was due to Bonahon and Thurston, just sort of doing two halves of the theorem. So this notion of interpolating between simplicial surfaces arose fairly early. So what's the point of this? So you control means whatever you think it means. It means you can control how far things go and so on. So here we are in this manifold. And we have, suppose that our surfaces that I was alluding to were actually those surfaces, determined by those triangulations. Okay? And I want to show that certain ones are homotopic to each other. So what I'm going to do is I'm going to try to push all of these things toward the core using elementary moves. Well, what do? This guy's a handle body. So I know that if I take any of these, and all of these are cores, so any of these surfaces has a loop in it which bounds a disk. Right? The map of this surface into the whole manifold is not pi1 injective. So every surface, contains a meridian. So it might look like this. You have our surface with our triangulation on it, whatever it looks like. And then in that surface, there's some, and then you can somehow understand the geometry of that wherever it's sitting in the picture. Inside there's some loop which bounds a disk in the manifold. And that loop might be enormously long, so maybe it looks like this. Okay, I'm not going to get it right, but you're supposed to think of this very, very long loop M, which is sitting in the surface. If I were to try to build a simplicial hyperbolic surface based on M instead of the original curve, it would have to be, M has no geodesic representative. If I actually built a simplicial hyperbolic surface and I tried to straighten out M, it would just collapse to a point, and I would have to hit the core. So what I do is I start with my original triangulation, and I start walking by elementary moves until I reach a triangulation which contains the meridian M. And I know, so first of all, this is a combinatorial theorem that these exist. That's due to Hatcher. And I know that if I did this, I have to hit the compact core. Because if I get all the way to the end, then the meridian is going to collapse. So the only other thing that can happen, and I can always make I should say, you can always do these moves, provided you are not too close to the core. If you're close to the core, you could run into the compressibility and things fall apart. So the idea here is that either you get to the core by getting all the way to the end, or something goes wrong. And if something goes wrong, it means that you're close to the core. So the conclusion is that every one of these surfaces can actually be walked step by step until it comes close to the core. And it turns out that once it's close to the core, there's a bounded diameter argument that says it's contained in some uniform compact subset. So every one of these surfaces can be pushed into this uniform compact subset without touching the core. And there's infinitely many of them. So actually, the only argument that some geometers know, including myself, is a compactness argument. So if you have infinitely many objects in a compact set, then they start to pile up somewhere. And it's not so hard to see. Actually, it's technical, but that eventually two of them will be so close together that they will be homotopic. And in fact, it'll happen infinitely often. So I think this is another observation which derives from Thurston's original work on these things. The idea of using this idea of this kind of compactness plus eventual homotopy. So infinitely many of these guys are going to be piling up and will be homotopic to each other. If they're homotopic here, they were homotopic to begin with, right? You push them over here, they're homotopic, and you push them back. So infinitely many of these, you can throw away the ones that aren't. All the rest are homotopic to each other, which means that all of these embedded surfaces were homotopic to each other, and therefore the manifold is tame. So that's roughly Soto's theorem. And the only question left is, what about step one? So why should there be this negatively curved surface? And this is where one needs ideas. And I think now I am coming close to the end, so let me sort of... so why should there be negatively curved surfaces near wherever I want? So how do I find negatively curved surfaces? I mean, I can do this, right? I can build these triangulations and then tighten them, like I said here, but then I don't know where they go. And I needed them to go to infinity in the end. So I need to control that. And the idea here is you put up barriers. So there are different versions of this, and different versions of this sort of if you say it very philosophically, it sounds like it's a general principle. But in fact, you can do certain things. So one kind of thing you can do is you can you can put closed geodesics in N. Well, in both cases, we're going to do that. So let me draw in one more time. So I'm adopting here the sort of schematic technique of Caligari and Gabbai. A closed geodesic is a point in this diagram. Suppose you take a closed geodesic in the manifold, and you have a surface somewhere else, then instead of just trying to tighten this surface in general, you could try to somehow tighten this in such a way that does not allow it to penetrate, to pass through these closed geodesics. So in Egel's work, the basic operation is you lift to a branched cover. And I should say that that statement, I mean, that sort of idea also comes from Canary's thesis, the idea of lifting to a branched cover. But so if you lift to a branched cover and you do it right and you chose the right surface, maybe your surface will lift to that branched cover too. And the thing that changes in your favor is the following. When you take a branched cover around some geodesics, you can very often get the surface, which used to be compressible, to become incompressible. And an incompressible surface, all this stuff works much better in the incompressible setting. You can sort of study once you have an incompressible surface, it's easy to find simple hyperbolic surfaces nearby. And moreover, but what happened at this locus? Well, when we take a branched cover around this, what do? We still get a hyperbolic metric, except now the cone angle around. So in the lift, if you have say a k/1 branched cover, in the sort of around the geodesic, you have a multiple of 2 pi cone angle. It's still a hyperbolic situation, it turns out. Just like for the simplicial surfaces, the 2 pi condition was important. So you still get a manifold which is like a hyperbolic manifold, and you can still make all this machinery work. So you can build up in this somehow, in this branched cover, you can build simplicial surfaces and then project them back down. That's one way to get them. And in the work of Caligari and Gabbai, there, I guess, I'm never going to get this. Okay, so they define something called shrink-wrapped surfaces. Which is essentially the following idea. You don't try to branch cover, you just try to make this surface as small as possible in the complement of these geodesics. There are various ways to make this technically work. One of them is to try to find minimal area surfaces in a homotopy class that's not allowed to penetrate the closed geodesics. And it turns out, so you can think of it, you have your laundry here, and you put up some clotheslines, and you let your laundry hang on the clotheslines, and or maybe you should be thinking about soap bubbles, or something. I guess there's soap bubbles in your laundry, so that's okay. Anyway, if you have geodesics, they don't really spoil. If you take a minimal surface and make it minimal, subject to the constraint of avoiding a geodesic, it still has this negatively curved property. That was the kind of observation that made all this possible. There are other ways of doing this. Soma worked out afterwards a kind of simplicial version, in quotes, of this minimal surface idea. But again, the point is that if the surface, say, encloses a collection of closed geodesics, and then you shrink wrap it, you'll get a negatively curved surface that still encloses the same collection. And so, if you can, in your original manifold, find a sequence of closed geodesics that go to infinity, then your compact core boundaries, when you shrink wrap them, will somehow, if you do it relative to the appropriate things, the shrink wrap things will also go to infinity, and you'll be able to use them. That's the rough idea. And the dichotomy which I erased. Oh well. So remember, there was supposed to be this dichotomy of geometrically finite versus degenerate. So if you're geometrically finite and you have a convex cap, then all the closed geodesics are contained in this compact set, and you won't find such geodesics going to infinity. But if you're not if you're not geometrically finite, if you don't have this convex cap, Bonahon showed that you could find geodesics going to infinity. And so this is exactly the dichotomy you're looking for. You can either all the geodesics are in a compact set, or they go to infinity, and then when they go to infinity, you can use them to hang these surfaces and then apply these sort of interpolation ideas. Okay. Now I want to caution you. This was like the trivial case of the theorem when you had an exhaustion by cores. There's a lot more work done, a lot more ideas in both cases, which deal with the general case, such as the example I gave in the beginning, where the genus of the exhaustion keeps growing, and then you have to understand the topology of these non-tame ends in a more intimate way before you can make any of this work. Okay, so maybe now I'm done. So, thank you.
Three-dimensional manifold with simplicial structure. Is there a procedure for determining what kind of a geometric structure you can put on that manifold?
Given a topological three-manifold, say, or so this is more or less Thurston's geometrization program. So you can study the fundamental group of a closed three-manifold, and if it contains, for example, abelian subgroups of rank 2. Then you can cut it along tori. There's a whole procedure. You first cut manifolds along essential spheres, and you get irreducible pieces, and then you cut them along essential tori, and you get pieces without any more essential tori. All these are finite procedures, and then the pieces, each one admits different geometric structures depending on the kind of group you have. So in particular, any manifold whose fundamental group is infinite and contains no non-essential tori is hyperbolic. That's the statement of Thurston's geometrization conjecture, and that was proven by Perelman. So now it's there. Yeah. Yeah, that's a good question. I think things get rapidly worse in higher dimensions. So, for example, Kapovich and Potiogailo showed in the 80s, I guess, that none of the basic theorems in three manifolds really work in hyperbolic three manifolds work in 4 dimensions. For example, there are finitely generated groups in isometries of H4, which are geometrically finite, which are saying this wrong, which have the property that even their boundary at infinity has infinite topological type. So what's called Alfort's finiteness theorem in 3 dimensions doesn't apply in higher dimensions. Somehow that you can get kind of infinite knotting in the 3 sphere, which translates into this kind of infinite topological type of the boundary. So that's one thing that goes wrong. Somehow we're also depending a lot on the fact that we have this quasi-conformal deformation theory of the sphere. The complex analysis describes the boundary theory for 3-dimensional manifolds, and there's sort of no corresponding. There's much more rigidity of the boundary when you go to 4 manifolds. So I don't really know the answer. The short answer is I don't know, but I think there are a lot of difficulties.